All right, we can put all our first we're now starting the next section in calculus. We can put all of this together by putting concavity, slope, and the function itself, putting it all together to actually graph entire functions just based on their derivatives and things like that, first and second derivatives. The first part of this next section asks us to find asymptotes. As a rule, vertical asymptotes occur when the denominator of a fraction is equal to 0. And we'll talk about horizontal asymptotes in a second. So you can see right here, if they give us this function and they ask us to find the vertical asymptote, we can do that by simply asking where is the denominator, in this case x minus 8, equal to 0. X equals 8 would solve that equation, and so there's your vertical asymptote. So this has a vertical asymptote at 8, and that can be useful if we're trying to graph the function. How about the next one? We have f of x equals 8 over x squared plus 64. Again, we just ask ourselves, when is x squared plus 64 equal to 0? And that is when we would have vertical asymptotes. Of course, this will never equal 0 because x squared is always positive. So that means this has imaginary roots, which means that for the real line, it will never equal 0. What that means for us is that this function has no vertical asymptotes. Okay, so that's pretty straightforward. Next part of the homework asks you to determine the horizontal asymptotes. Horizontal asymptotes are end behavior of a function. So what's the function doing as it gets to the ends towards positive infinity and towards negative infinity? And there's generally a rule for that. If the degree, let's say we have ax to the m over bx to the n, right? And then plus a bunch of other stuff, plus or minus a bunch of other stuff. All we care about are the two terms that have the highest degree, okay? If, here's how it works. If m is equal to n, in other words, if the degree of the top is the same as the degree of the bottom, then that means that the ratio of a and b is the horizontal asymptote. Okay? If m is greater than n, meaning the degree of the top is bigger than the degree of the bottom, then that means it will explode and diverge, that's what we call it, either to positive infinity or negative infinity, depending on if the function is positive or negative. If n is less than m, meaning the degree on the bottom, oops, I'm sorry, got that backwards. If the bottom degree is bigger, in other words, if n is greater than m, then that means that it will converge to 0. And so the asymptote will be, the horizontal asymptote in a way will be 0 because we're just going to converge to 0. Finally, if m is 1 bigger than n, if m is 1 bigger than n, then that means we get what's called a slant asymptote. Okay, a slant asymptote. And that's where we're going to, sometimes this is called an oblique asymptote, I've seen it called. Our homework is calling it a slant asymptote. But it means that our graph is going to be doing something like this, where we've got a graph and there's some diagonal asymptote that the graph does funny stuff, and then at the end of its life, it approaches some diagonal asymptote. So maybe we've got a vertical asymptote there, but then at the end behavior, it kind of approaches this diagonal asymptote. So anyway, those are the rules. Let's apply them. Check out this function right here. Determine if there is a horizontal asymptote. So on this problem, we have that the asymptote is going to be our degree on the bottom is greater than the degree on the top. And so that means the horizontal asymptote is just going to be y equals 0 because it's converging to 0. The degree on the bottom is bigger than the degree on the top. As x explodes to infinity, we get a smaller and smaller fraction that forever approaches 0. On this one, notice that our degree is the same for both of them. And so what we can do is, if that's the case, then the horizontal asymptote is just a over b. Everything else will end up canceling. As x gets very, 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 very big, we'll always be approaching this fraction. So in this case, the horizontal asymptote is just 8 over 20, which of course reduces down to 4 over 5. So that's all they're asking for on these asymptote ones. It's pretty straightforward. Now I can actually prove all of this with limits. The homework doesn't ask us to do that, so I'm going to skip over this right now. But if you took a full calculus class, you would see that this can be proved by basic limits and taking the limit as x goes to infinity. That's all for now. Let's look at some more examples in the next video.